Information systems, working principle of automated system. In this video, we'll talk about the working principle of automated system inside power generation and smart grid information system. At the end of this video, you will be able to describe the process of information in automated system, let's consider a SCADA system that supports the automation of a power plant. The operational core of a SCADA system is the remote terminal units, or the programmable logic controller. The principle of controller is to receive information from the sensor, to process this information, to activate actuator accordingly. This principle takes its origin from control system theory that studies the behavior of dynamic systems. This simplistic control structure can be represented as an open-loop system, where the action of the controller is independent of the process variable. The process variable is the measured dimension on which the actuator acts on. Take the example of a hydroelectric dam. A pump fills the dam to store water. The process variable is the volume of water. If the control action of activating the pump is only based on a timer, it is considered as an open-loop system, as the control action, pumping water, is not correlated to the process variable, the volume. This can lead to catastrophic situations, such as an overflow leading to a flood. Open-loop systems are opposed to closed-loop systems, as the control action is dependent of the process variable. In the case of the hydroelectric dam, a gauge would measure the volume behind the dam and feed back a signal to ensure the controller outputs maintain the volume of water in the dam in the defined range. Automation based on sensor and actuators connected to programmable logic controller requires to set up electrical cabinet. In this cabinet, the PLC is here. One of the current trends is to embed controller with sensors or actuators to facilitate the access to unreachable places with wireless connection. These embedded devices are similar to computers, but depending on the type, form factor, and shape, they can be quite similar to a microprocessor. Let's check them further in detail. Both microcontroller and microprocessor possess calculation capabilities. In addition, microcontrollers have non-volatile memory to store the program, also called firmware. They have volatile memory to store temporary data needed by the program. This memory is erased when the microcontroller is switched off. The microcontroller also integrates a clock that gives the rhythm to the CPU, and which conditions the number of operations done per second. Finally, microcontrollers possess general-purpose input and output, also known as GPIO. To summarize, microprocessor, also qualified as CPU, is limited to do elementary operation. It does not work alone. In opposite, microcontrollers integrate microprocessor and possess everything to do what it was programmed to do. The conclusion of this quick comparison is that form factors and shapes are not reliable indicators. A microcontroller is a chip like this ESP32 Pico chip from Expressive. This is also called a microcontroller. It is also an ESP32 from Expressive. It is confusing. The difference is notably the onboard antenna, weldable pins with their functionality indication, and some surface-mounted component associated to these pins regulating voltage and protecting the microcontroller. In fact, the first microcontroller is integrated in the second one. The interest of microcontrollers is general-purpose input and outputs. It is a pin that can be programmed to be a digital input or output. They can read or write two values: low, equivalent to 0 volts at the entry of the pin, and high, equivalent to either 3 volts, or 5 volts at the entry of the pin. Practically all pins are general-purpose input and output, except some power pins, ground pins, and not allocated pins. However, some pins possess special features. Analog pin, or ADC for analog to digital converter, transforms the input voltage between 0 to 3 volt, or 5 volt to a range between 0 to 1023. DAC pin for digital to analog conversion pin is the exact opposite of an analog pin. It transforms digital value defined by the microcontroller to a voltage. Serial pins are by default configured to support standardized communication with peripheral devices such as sensor, screen, SD card reader, through standards like UART, I2C or Ethernet. What about programming? Although microcontrollers are quite versatile as they can be programmed, how is it done? There is one way to program a microcontroller, using the Universal Asynchronous Receiver-Transmitter protocol that is natively interpreted by microcontrollers. It requires a USB adapter plugged on a specific pin of the microcontroller. Over the past few years, the commercial success and popularity of Arduino changed the electronic ecosystem. The core of Arduino is a common microcontroller, the Atmel Atmega 328P. The reason for this success is the fact that it facilitates the programming process. It uses a standard USB connector, a simple connector to plug any devices on it, and a simple development environment. Nowadays, every manufacturer proposes development boards that provide DuPont wire connectors for easy prototyping, a USB connector, a chip to convert USB signals to UART signal, microcontroller with wireless connectivity, Wi-Fi. In terms of environment, to program these microcontrollers, Arduino gains in popularity due to its simplicity and accessibility. However, it's not a real integrated development environment. Another tool that is gaining in popularity, Platform I/O, that is cross-microcontroller and cross-IDE. It is a plugin for Atom or Visual Studio Code. Benefits are notably the real-time code checking, possibility to automate test, separated development environment for each project. Another alternative is Xerinth. In terms of languages, Arduino and Platform I/O allow to program MCU in C, whereas Xerinth uses Python. Several key concepts were introduced to understand automated system. Control theory concepts with the distinction between process variable and control action. Process variable is a measurable parameter of the system. Control action is the action triggered by controller that influences the system. There are two control loops, open loop and closed loop. Open loop systems involve independent inputs and outputs. In opposition, closed-loop systems are based on feedback. It continuously modulates control based on the value of the process variable being controlled. To control actions and receive feedback, controller and microcontroller that are small computer with GPIO can be programmed accordingly. The only limit is the technical specification of pins. To simplify development and experimentation, development board can be preferred from microcontroller chip, as it simplifies power supply, voltage tolerance on pins, programming connector, USB. Thank you for watching.